making this content. I work for Bishop Fox, but I now work for a ride-sharing service called Uber. I also do post about security on my blog at thehackerblog.com, or hit me up on Twitter at IamMandatory. They say you're supposed to keep your public keys public, so here's my Signal fingerprint. If you're texting anybody else about 0 days, it's not me.
And I'm Mike Brooks. I go by Rook, which comes from my last name, just without the BS. I participate in Stack Overflow and Security.Stack Exchange. I think these are great communities for security professionals. I recommend that others participate.
So we're at an interesting point with the web and the way that things are architected when it comes to kind of like the Alexa top 10,000, kind of these big web applications. It's pretty rare nowadays where you'll have just like a single web page that has all of the resources hosted on just that one website. They all make use of like different third-party services such as Google Analytics, AWS, all these different things to kind of bring together this final product that you actually view when you like go to Facebook.com, for example. And so what's interesting about this is you actually end up implicitly trusting all of these third parties just by using the website itself without you even knowing or having any knowledge of these third-party services at all. And so this brings into consideration some of the interesting security implications when you have a vulnerability in one of these third parties. So specifically, we're going to be talking about content delivery networks. And what are content delivery networks? They're basically, you'll have things like Akamai, who basically have these huge networks which you can use in order to serve content quickly to your users. So you take advantage, they'll serve content for you, and you save on bandwidth. You can like outsource it to them. And of course, when these operate invisibly in the background, I doubt you guys can name off all the services that use Akamai because they're just invisible to you. So many people, probably your parents, think of the internet in kind of this way. They think, I type in foxnews.com into the web icon thingy, and that must go off to like Fox, and like Fox gives me back the web page, and like that's it. If they even know have like a general idea of how that might work. But of course, we know that that's just not the case anymore. We see that probably Fox News, maybe they want to gather analytics on how their users browse the site. Of course, they'll include some JavaScript from Adobe for Adobe Analytics. Maybe they don't want to host a big blob of JavaScript. It takes away from their bandwidth. They'll use jQuery to host that content. Maybe for all of their images, they'll use something like Akamai in order to serve all that, like the heavy lifting stuff for them. And maybe even their DNS is actually managed by a third party or like Dyn DNS or something. So all of these things kind of come together to give you this final product that you see. So this puts us into a very interesting position where we have kind of a couple core CDN products that all of these different websites kind of implicitly trust. So what happens when you find a vulnerability in one of these core CDNs? The answer is the impact is severe and it's far-reaching. So we're going to start right off by showing you an example of the hack. And this example is with Ralph Lauren. So for those of you who don't know, Ralph Lauren is kind of a high-end clothing retailer. They sell like accessories, purses, what have you, for kind of high marked up rates. So you have a user browsing that site, and after they log into this website, they navigate to this third-party website, which is just some arbitrary attacker-controlled domain. And after they do so, they go back to the original website, and they notice something odd has happened. So when they actually navigate around the site more, they see something's been added to their shopping bag. What could that be? And the answer is we've added a very expensive alligator handbag, almost $29,000.
That's one fancy alligator.
To your shopping cart, and without you having any knowledge of this. So this is quite concerning. How does this happen? We have another example here, and before I go into this, I would just like to point out that mad props to Microsoft. When we did this talk at Black Hat, they actually reached out to us beforehand and were like, hey, we know you're giving this talk. Are we affected? Is there anything we can do to get patched before you guys even give this talk? And of course, we identified some endpoints and like helped them patch it. So massive hands off to those guys. Really, really nice stuff. So here's an example. We have a user browsing to actually a subdomain of So we have live.com. It's a subdomain of a Microsoft-owned domain, and we see that they go, they get the standard protect your PC. They're probably going to go download Microsoft Security Essentials, but when they actually go to get it now, they don't get Microsoft Security Essentials. They get command.exe. So how is this happening? How are they serving up this random binary? And the answer is a vulnerability in the CDN that they use.
So what happened here? We used an attack chain comprised of server-side request forgery and a remote Swift include to control the content delivered by the network by Akamai. So why attack chaining? Why is attack chaining useful? Attack chaining allows us to increase the impact posed by bugs. Now, a real-world example would be, let's say you're trying to break into a building, a home. Let's say you find that the gate to their backyard is open, and you walk into their backyard, you find that there's a ladder in the backyard, and use this ladder to get onto their patio or their, and then once you're up there, you find that one of the windows is open, and now you're inside the building. So that's a physical attack chain that allows you to break into a building. So what about how would you break into a ivory tower? Well, you would use an ivory ladder.
Those poor elephants.
Poor elephants. So in order to find this issue, we need DNS. DNS holds all the keys. It shows us trust relationships, and it revealed this issue to begin with. So this particular vulnerability in Akamai has been around for a long time. It went undiscovered for quite some time, and I think there are a couple of reasons for that. One is that penetration tests have a divided scope. Usually, penetration tests are worried about load balancers, HTTP servers, databases, and administrative interfaces. And the external supporting services, such as Gmail, CDNs, Cloudflare, a lot of Amazon AWS services are left out of scope. So in the case of Gmail and these Google services, they have a bug bounty program, and you think that they would be pretty secure, but all too often they have very weak passwords, and these are left outside of an assessment. This particular issue is affecting the external supporting infrastructure, and I think that's a contributing factor. Another part of it is DNS, what tools we use to map out our targets. So there are a number of DNS tools that help you in the footprinting process. One of them is DNSdumpster.com. Now, this service has an artificial limitation. It returns a large number of DNS records for your host, but it's limited to only 256 records. Now, 256 records is nice, but it is nowhere near the number of records that you'll find on the Alexa Top 10,000. So there are other tools, DNS Recon or Fierce. These are older brute force utilities that help enumerate subdomains. I think that I don't like the limitations in these tools, so I wrote subroot. Just as a show of hands, are there any subroot users in the crowd? Oh, a couple. Okay. Well, I'm the project maintainer of this of subroot, and we have over 90 forks now on GitHub. And the usage is simple. In this case, the first command here is running subroot against Google. -p prints out all of the DNS records it finds, and -s uses in this case, a large list of subdomains. There's also a -r option, and -r uses open resolvers as a kind of proxy between you and the authoritative name server, such that none of your traffic goes directly to your target. So this is a pseudo-anonymous feature. It also is significantly faster because it bypasses the DNS rate limiting, which is prevalent in all modern DNS servers. So now, subroot is a metaquery spider. So what is a DNS metaquery? Well, subroot uses two different metaqueries. The first one is an AXFR. AXFR is the easy button. If AXFRs are allowed by the authoritative name server, you get a list of every DNS record that it is responsible for. Done. Now, what subroot does is it tries each DNS server responded by the NS record, because one of them may be misconfigured to allow AXFRs. But something like 99% of the time, this is going to fail. It's still worth trying. So then it falls back on any metaqueries. Now, any metaqueries return all records of all type for a particular name, but you still have to find out what those names are. So you can do metaqueries on the command line using dig. In this case, dig anygoogle.com using 8.8.8.8 returns 24 different record types. There are A records, quadruple A's, NS, type 257, MX, some interesting stuff to look at. So what subroot does is it does any query, and it matches all of the data segment against a regular expression looking for subdomains of interest. Now, this is future-proof. I don't care what the type of record it is. I just care that there's a DNS, there's a subdomain, or some domain within the data type, and then it recursively crawls these types. So what does that give us? When running this against Google.com, we find over 3,000 DNS records. I don't know of any other tool, any other open source tool. It doesn't matter. I don't know of any other way to get more than 3,000 DNS records on Google.com, and that is a bad thing. There are a lot more than 3,000 DNS records, and I am looking for ways to find more. We need better DNS tools so that we can find vulnerabilities in content delivery networks, so that we can find vulnerabilities in supporting infrastructure. So I encourage others to send me pull requests to Subroot, or fork me, or find ways to find more DNS records. So let's look at the breakdown here. Overwhelmingly, Google's returning A records. Now, these are just a DNS record pointing to an IP address, and the reason why Google has predominantly A records is because Google hosts all of their services in-house. They use their own content delivery networks, their own email, their own VoIP. Everything is in-house, and so it's all pointing to their own systems. Now, I think this works really well for Google. They're a very hardened target, and they were not vulnerable to this particular issue. But there are other records returned. CNAMEs, quadruple A's, SRV records? No error, type 257? What are these? Okay, so type 257 is a new DNS record type, and it is used in DNS certificate pinning. It is the SHA-1 hash of the issuing CA cert used by Google. In fact, this is a way to help defeat malicious CAs issuing certificates for Google.com. Now, why is this a problem? Well, Google is running into trouble with malicious governments. In this case, the Chinese government is notorious for using their own certificate authorities to issue malicious certs for Google's domains. So DNS not only shows us trust relationships, it shows us that our target has trust issues, that they don't trust people. And that's important. It's very interesting. Now, there's another emerging standard in DNS, and that's called DANE, or DNS-based authentication of named entities. This is a way of replacing our broken PKI with using DNSSEC as a trusted party for distribution of certificates. I think DANE has the potential for solving this problem of malicious issuing malicious certificate authorities. And in the future, I think it will solve this problem. But we don't live in that future. Not yet. Now, other records returned were SRV records. What are SRV records? So in this case, SRV records follow a common pattern. In this case, CalDAV is running on TCP, and it's running on port 80 and pointing to calendar.google.com. There's also LDAP, which is running on TCP port 389 and found at ldap.google.com. So service records are a way for applications to find the server that they use. So when you plug a VoIP phone into your network, how does the VoIP phone find its VoIP gateway? It uses SRV records. How do Windows machines find their domain controller? SRV records. Now, something else that we found when we were mapping out our target in a pen test was we found this strange CNAME chain. So we found that some subdomain of our target was pointing to Edge Suite, and another CNAME pointing to Akamai, and then finally an A record pointing to an IP address. Now, we started mapping out these DNS records not only for our target, but for some of our other clients, and then in this case, Facebook. And we noticed that this common pattern existed on a large number of sites. This is one of the first indications of the vulnerability that we are going into. So Subroot can also be used on an internal network assessment. And that's why I built subroot.exe if you're on a Windows system or if you're using it in post-exploitation. So in this case, subroot.exe is being run against the subdomain on an internal network, and the internal name servers will return, will give you more information about what's running. So in this case, we're running it, we found 19 domain controllers in this network. That's huge. Now, each of the domain controllers are named after hockey teams, the Rangers, the Sharks, the Canucks. How much do you want to bet that one of their passwords was a hockey player name followed by his jersey number? The chances were good. Now, DNS can also suffer from information leaks. So in this case, a common DNS misconfiguration opens the door for CWE 203, which is information disclosure through discrepancy. This is the kind of catch-all for disclosing information. So what does that look like? Now, what Subroot does is it tries to look up a subdomain that it knows doesn't exist, some random large sub. And while it's looking up other domains, if it ever gets a discrepancy, some other response, it records it. And so in this case, when we're running it against our target, we get these no errors. So I say, hey, domainkey.legitbank.com, does that exist?
So the server would reply with, I can't confirm or deny the existence of that data, but you definitely didn't throw an error when you requested it.
Fishy. So in this case, subs of domain key are public keys used for cryptographically signing outgoing email. By having domain key, we know that our target is cryptographically signing email using DKIM. Awesome. SCI, VCS, dev, what are these? Internal.legitbank.com. Now that's interesting. So let's enumerate these subdomains. So subroot takes its output files as inputs. And so we can specifically rerun subroot against all of the no errors that were returned. So ldap.sci.legitbank.com. Awesome. So we know SCI is its own domain under legitbank.com. It has a domain controller that resolves to an internal 10.IP address. Wait, we just found the IP address of their domain controller from an external assessment. But we can't access it. It's 10. It's still a information disclosure vulnerability. This misconfiguration should not exist in a production environment. What about internal? So internal, we found two subs. Accounting.internal.legitbank.com. I would love to access the bank's accounting system. And monitoring, that's awesome. But I can't access these 10 dots from the external. Or can I? This brings us to server-side request forgery. So SSRF is about trust. So our target, our server, legitbank.com, needs to trust other services. It may be a part of a virtual private cloud deployment. It has other internal HTTP servers that it relies upon, internal databases, and internal administrative interfaces. SSRF allows us to make requests as the server and access these internal resources. So why does SSRF exist in the first place? Why would anyone have this vulnerability? Well, one reason why it may exist is to circumvent the same origin policy using something called a cross-domain proxy. Now, when you search for cross-domain proxy on Google, the first two results are SSRF. Now, specifically, the second result here, PHP cross-domain proxy, we'll go into in a bit. Okay, so what tools do we use for exploitation and identification of these issues? Now, there's NCAT, which is the latest version of Netcat, and I highly recommend updating. There are new features in NCAT that are great. There's also httpbin.org, which is an interesting HTTP server that gives you a variety of responses back. Now, personally, I never use HTTP bin on a pen test because I want my O days to be private. So I run my own burp collaborator. And that way, all of this asynchronous or callbacks I receive, and I'm not worried about a third party finding my O days. So in this particular case, burp collaborator would easily find this issue of PHP proxy. So now, PHP proxy accepts one parameter. It is in this case, URL. And so this URL, what happens if we put in localhost 631? So localhost 631 is an HTTP server running the cups daemon, which is a printer daemon, and this runs as root on localhost. Now, older versions, and what this shows is that we're able to access a localhost daemon from the remote internet. We're able to break a trust boundary. We should not be able to access this interface. Older versions of the cups daemon were vulnerable to shell shock, and exploitation of shell shock in this context leads to remote root. However, 1.53 was not vulnerable to shell shock, unfortunately. So, what else can we do with this? So we can turn this particular issue into a port scanner to scan the local internet. Now, burp intruder has a cluster bomb mode. And what cluster bomb mode does is, in this case, we have two insertion points, and we provide it two lists, and it permutes through every combination of these two lists. This is very helpful in performing a brute force attack, where you could give it a list of usernames and a list of passwords, or in this case, a list of local IP addresses and common ports with HTTP servers, 80, 80, 80, etc. What did we find? On 192.168.201.1, on port 80, we found a Cisco switch with a default username and password, an all too common finding on an internal network assessment, or in this case, an external network assessment that just broke into the internal network. So, what else can we do with SSRF? Now, legitbank.com is a Nginx load balancer, and it is a gateway for a number of HTTP servers that are hosting www.legitbank.com. Now, is there a way to fool this system into accessing accounting.internal.legitbank.com? There was. In this case, we create an HTTPS connection to legitbank.com, and then we change our host header to access accounting.internal.legitbank.com. Now, what this returned was a 401 unauthorized. And it had a trivial username and password. Now, accounting.internal.legitbank.com allowed us to transfer money arbitrarily between accounts. It was on a protected network on their internal system that was segregated from the rest of their internal network. However, their web server needed to access accounts because that's how it moved money around for the users. So it had a trivial username and password because they weren't expecting employees to access it, or in this case, an external pen tester to access it. So yeah, simple HTTP basic auth, and we were able to log in and access this RESTful API. So SSRF and load balancers, I highly recommend looking for this issue. I think that this is something that is much more common, and I recommend that other pen testers look for this type of defect. So now other questions to ask yourself when exploiting SSRF. Can I access a protected resource, such as an internal server? Can I turn another vulnerability, such as XXE, into SSRF? Well, you can using a DTD system to make HTTP calls. Now, can I access internal IP addresses, such as ones enumerated by subroot? Could I access virtual private cloud instances, maybe S3 or MongoDB? MongoDB, by default, doesn't have a username and password, and SSRF may expose private collections. Can I connect back to a host I control, such as Netcat? By connecting back to my own server, I'm connecting to a HTTP client that's running on the web application. Now that client, that web application, might be running an old version of the OpenSSL library, and I could exploit Heartbleed on that system. So even if the web server itself is patched, libraries run by the application may still be affected by Heartbleed. Or can I load an arbitrary content, such as a SWIF, on my target domain?
I'm going to pick this microphone up. This stand wasn't made for tall people. All right, so we're going to kind of switch gears here. We're going to talk about Flash Remote Swift include vulnerabilities. Flash, the way that it works, the way that you can externally... No problem. So the way that Flash works when it loads external Swifts is actually quite different from the way, for example, JavaScript works when you take a third-party JavaScript file embedded in your page. And this leads to some interesting exploit scenarios, which we're actually going to show you. So before we get started, we want you guys to actually go out and actually, find the stuff yourself. So here are some tools that you can go about doing this with. One of them is this cross-domain.xml proof of concept tool. Now what this is just a Swift that you can upload to an example host, and it lets you set up requests in Flash and then execute them and then see if they are successful or if they failed for a security reason, and then you can debug basically your flow with this. Now after you've successfully figured out your Flash vulnerability, you can actually use something called Flash HTTP request, and this is a bridge that allows you to perform requests in Flash via JavaScript. So instead of writing like a lot of ActionScript, which is just a bad time in general, you don't have to do that anymore. You can just use JavaScript, which is less bad. Not great. So another tool, if you actually want to go about finding these vulnerabilities in Swift, is something called JPEX, and this is a tool that Mike actually recommended to me. I was using some terrible HP tool. This is so much better. Basically what it lets you do is it lets you decompile, get the source, view what's going on. So they have some great debugging features. In addition, you can actually edit the source code, recompile on the fly, and just do some really great debugging with Flash. So if you want to find Swift bones, this is a great tool to be using. So after you've got your working POC, you've got the vulnerable Swift, you want to find out who's using this, you can actually use a tool called Search Diggity. This is a tool developed by one of the founders of Bishop Fox, and it's great. So you can actually utilize things like Google and search engines to go out and find who has a Swift and kind of enumerate your larger attack surface.
Search engine hacking is alive and well in 2015 with Search Diggity. I highly recommend checking it out.
Yeah, it's an awesome tool. Right. So I talked earlier kind of comparing Flash to JavaScript. So to kind of give you an idea of why Flash is odd in the way that you embed it into your page and how it operates, we're actually going to compare it to JavaScript. So we're going to show some examples from both and kind of show you in contrast. So we're going to stop for a second here and we're going to talk about something called the same origin policy. How many of you guys are familiar with the same origin policy or have heard of it? Awesome. A lot of web hackers here. Great. So what the same origin policy does is it's kind of a fundamental pillar of web security. And the idea is if you had, for example, your Gmail open, right, and then you navigate to my blog, should my blog be able to read your email? The answer is, of course, no. And the web doesn't allow you to do that. And the reason for that is each site has its own origin. All an origin is simply like the protocol, the hostname, and the port of like a certain website. So for example, in the case that I just talked about, you'd have https www.gmail.com, you would have https thehackerblog.com, and if Gmail tried to request content from my site or vice versa, it wouldn't work because those origins are not the same and it would be a violation of the same origin policy. So this is what sandboxes all these different websites from accessing each other's data. So what is the difference between the way when you do remote includes with JavaScript and Flash? So in JavaScript, when you do, for example, a script tag and you specify like a third-party resource hosted on a completely separate domain, when that script actually executes, it executes in the context of the page that did the including. So this is actually completely opposite from how Flash works. So when you do Flash and you include the SWIF in your own page, that SWIF actually executes in the context of whatever's hosting that SWIF. So say you had like thirdparty.com, right? And it's hosting the SWIF. You include it in your page, it's still executing in the context of thirdparty.com. And that's kind of that's the difference between the two. We're going to show you guys some examples to kind of drive the point home. So what does remote JavaScript inclusion look like? You've probably seen this if you've viewed this source of the web page before. You have a script tag with SRC and you have a thirdparty.com. This is on legitbank.com. So basically when your browser is parsing the page, it grabs this remote JavaScript file, pulls it in and executes it in the context of that page, right? So what's in this JavaScript file? It's just a simple script that basically prints the executing origin. So you can see, what is the script executing as? Of course, when we go off to run this, because of the way JavaScript works, when you include it onto your page, it actually executes in the context of the page that did the including. It doesn't execute in the context of third party. It executes in the context of legit bank. This is important because as we see with Flash, we do an object tag, right? And we have a third party and we include that SWIF onto our own page. Now, what's weird about Flash is when you actually include that, it actually executes in the context of thirdparty.com, the site that's hosting the SWIF, not, legitbank.com, which is actually has it on its page. So to show you guys an example of this, to kind of prove that this works, we have a secrets.txt file on thirdparty.com. We're going to show this flow actually happening with a short little video here. So this is that cross-domain.xml proof of concept tool that I talked about earlier. So we're just going to set up a very basic request. We're going to say, let's get a request to that thirdparty.com secrets.txt file that I mentioned earlier, and we'll see if it works, right? When we go off to do it, it does work, and this makes sense because the SWIF is executing in the context of the site that hosted it, not of the context of the page that it's running on, which is legitbank. And we turn around and we try to do a request to legitbank.com. It doesn't work. The reason being is the SWIF is executing in the context of third party, not of legitbank. So that's the difference. So there are definitely some scenarios where you would want to open up other sites to access your data off your site. Maybe you have like a third-party widget that needs to pull profile information to display something to the user via this third-party service. You can actually open that up. And the way that you do that is generally you use a cross-domain.xml file. And usually this is like a XML document that's placed in your web root. And it basically lists off via allow access from, and it says, what domains I trust. So I can say like, oh, thirdparty.com is cool. If my users are logged in, they can pull the data and they can parse it, do whatever they want with it. But this is a large level of trust, right? You're trusting these domains to handle all of your users' sensitive data. So you want to make sure that this is like solid, that these, the attack surface is minimal here. But that's never the case actually with cross-domain.xml files. For whatever reason, wildcard usage is allowed and it's incredibly commonplace. And that's not just like a made-up statistic. So we pulled from the Alexa top 10,000. Sorry, I'm going to talk about this example cross-domain to drive the point home. So we have like 2 entries here, right? Seems like pretty small. You're like, okay, well, 2 entries, that's not a whole lot. But actually, with these wildcards, that means any subdomain of either legitbank or thirdparty.com can grab all the user information from legitbank.com while the users are logged in. This is actually a very large attack surface. I mean, these subdomains could be pointing anywhere. They could be any third-party service. Could be potentially thousands of entry points then an attacker could, get a SWIFT on, for example. Right. So like I talked about earlier, we didn't just pull this statistic out of our, out of nowhere. We actually pulled the cross-domain.xml files from the Alexa Top 10,000. Those that had it, and this is actually like really close on the mark, 75% of all sites employed this star.domain. Like they did all wildcard of all subdomains, right? And this is incredibly dangerous, right? So you have a bunch of sites walking around trusting all the subdomains of like a main domain and exposing, potentially thousands of endpoints, which could compromise the security in their main website. And this is super dangerous, and it kind of sets us up for some problematic behavior, as we'll see. So you're an attacker. You're viewing the cross-domain.xml file. You want to compromise the security. What's the first thing you do? I noticed that not a whole lot of you raised your hand with subroot. That's so sad. It's a great tool. You can actually just plug this domain that you want. So example, we had 2 entries in here. We had third-party, legit bank, just plug them into subroot. It'll print out all the subdomains of these hosts, right? Then you can go and independently audit each subdomain, see if you can get a SWIFT on there in some way. And then if you can get a SWIFT on any subdomain that subroot prints out to you, you can compromise the security of legitbank.com. So I talked about Flash, includes security. What does that mean? What does that look like? And we're going to give you an example here, which is in an application called FlowPlayer. So what is FlowPlayer? It seems to be a very common convention in Flash that you have a video player. So all FlowPlayer is it's a Flash application that plays videos for you, but it gives you kind of this extra functionality where you can kind of customize the look of the player. You can, you can make it different colors. You can change the functionality by just making arbitrary Swift plugins that you can load into the player. Unfortunately, with FlowPlayer versions below 3.2.16 and up to that version, you could actually load plugins from arbitrary domains, which is actually incredibly dangerous behavior. So what this means is if you have the FlowPlayer Swift on your website, any third party can include that in their own page. They can load a plugin to hijack that Swift, and they can operate as if they were coming from your origin, right? So we'll see how this comes back to bite us in a flow later, but here's how you would set this up, basically. So we have an embedded Swift of this FlowPlayer on legitbank.com. We want to include a third-party plugin in here, so we set it up in JavaScript, specify the full URL, and then this Swift just takes full control over the player. So this is obviously incredibly dangerous behavior. Eventually, FlowPlayer was like, "All right, this is a bad deal. We can't do this." We don't want our users to be walking SOP bypasses. So what it turned out to be is in 3.2.18, they actually introduced some code that says, all right, well, it has to be on the same domain or it has to be trusted in some way. They added a lot of verification code to basically prevent arbitrary plugins from just hijacking this player. So they added a bunch of code that parses the plugin's URL to check if it's trusted or local. However, and this is actually a pretty interesting story.
So FlowPlayer, one of their problems is they wrote their own URL parser. And it's a common problem for developers to think that parsing URLs is very simple. But there's a whole chapter devoted in the Tangled Web to just problems with parsing URLs. This is an amazing book. I love this book. This is the Holy Bible for web app hacking. And after reading this book, I was like, yeah, I am totally prepared for bypassing some URL parsing bugs. So I just started at the very top of the FlowPlayer's URL parser, and I found a SOP bypass, or I found a way to include arbitrary Swifts, and then I sent the link to the code over to my friend Matt here, and said hey, can you find my bypass? But
I actually ended up finding a completely separate bypass when I thought I'd found his.
So the bypass he found specifically is on this line here. Now, you may think that there may be some other problems here, obviously, but this one is interesting. So in this case, they're looking for a string that starts with / and saying, oh, okay, well, that's probably a local domain. It's probably on the local domain. This should be fine, right? Well, no. You can, if you start with 2 /, it inherits the protocol of the domain that's loading, or so in this case, the protocol is HTTP, so it inherits HTTP and makes an HTTP request to attacker.com and loads the Swift just fine. So the one I found is here. This is some interesting, it's kind of complex code. And what it's doing is it's trying to separate the beginning of the scheme, the protocol scheme, with the domain. And the problem is here. It's looking for 3 forward slashes as the beginning of the scheme. And we can bypass that by saying attacker.com, 3 forward slashes, which tricks the URL parser to think that attacker.com is part of the protocol. And then we use a // to remove legitbank.com and then just load our Swift normally. The third one is more general. So in this case, we're turning an open redirect vulnerability to trick the URL parser into loading our Swift remotely. Now, this is a more general bypass for Swift remote include vulnerabilities, and that's why I include it. This can take a remote or a open redirect vulnerability, which is typically low or medium risk finding, into a high risk same origin policy bypass. And so this is a more general issue. There may be more bypasses, but 3 is a good number. 3 is a good number. So
cool. So what does this mean for us as attackers, right? What this means is if any domain has the flow player Swift, like anywhere on their website, you can basically execute Flash as if you were coming from that website. Kind of an interesting side note here is we actually reached out to the flow player guys and we're like, hey, you got mad vulns, you need to fix this. This is really dangerous. And they actually responded with, oh, you know, Flash, it's kind of dead. Like, we have an HTML5 player. Why don't you go off and use that? So it was not exactly a great response. So actually, they're not going to patch this. So any site that has this is still, like, you can just take advantage of it, right? So this is kind of a complex flow. We're going to walk you through it. So here's an example where we have a user who's logging into legitbank.com. They're managing their financials. You know, they're checking their credit card statements, whatever that may be. After they authenticate, they somehow navigate across the web and they hit our attacker page. And what our attacker page goes off and does is it includes a Swift from legitbank.com with this flow player and, you know, in an object tag. And we load it onto our own page. So once we've done that, we actually set it up with JavaScript and we include our, you know, plugin to hijack this thing via some of the bypasses, or if it's an older version, we can just load it. And we can hijack this Swift, which is loading in the context, remember, of legitbank.com. So what does this mean? So now that we've hijacked this Swift, we can actually go right back to legitbank.com and we can just start pulling data. Why does this work? Because the Swift is actually it's executing in the context of legitbank.com. So there's no same origin policy like violation where we're doing that. It's same origin. So it's completely fine. So now we're going to kind of tie it all together. Here's where like the big exploit kind of comes together and how we were able to, you know, compromise a lot of these large sites. So this is about Akamai's Edge Suite. So like, what is Edge Suite? So edgesuite.net is actually a domain that's used in Akamai's content delivery network. More specifically, it's actually a product of their free flow service, which is a super deprecated, kind of when they were a young CDN back in the 90s, they were just kind of trying stuff out. And free flow used to be how this all worked. Unfortunately, due to, you know, sites just not moving forward, and a lot of like old functionality still working, many endpoints still have this completely enabled. And you can actually still go out and abuse this. And some people like can't patch because they're dependent on this old infrastructure. So the way that this works is you'll actually take your own subdomain and you'll map it into Akamai's network. So when they hit this subdomain, they're actually hitting Akamai. They have no idea. It just looks like their domain, right? So remember earlier Mike talked about like the Facebook setup, right? So you have this interesting like DNS configuration. So you have like akamai.example.com, which is a CNAME towards x.example.com.edgesuite.net, yet another CNAME into the subdomain of akamai.net, and you have an A record that actually hits an Akamai endpoint, right? So this is the kind of setup that we saw before. So like, why do people do this? Why use Akamai? And the reason is because of this. So when you have a user who wants, for example, an HD image of a cat, which is kind of my view of the internet traffic at large, you know, it's probably true actually, but they grab the image off akamai.example.com, kind of invisibly in the background, they're hitting Akamai. Akamai goes off to example.com, they grab that image, they store it, they catch it locally, they distribute it, and then, you know, return it back to the user. And so why do this, right? It's like an extra hop. So like, what advantage do they get out of this? And the reason why they do this is the next time somebody comes along with kind of this hunger for felines, they actually just skip a whole step. So it doesn't even go off to example.com. It's like, cool, I got it in my cache, I'll just serve it to you right away. You know, they can be geographically close, speed that up, right? That's the advantage that you get with Akamai. So another odd piece of functionality that, again, was kind of established in the 90s is something called an ARL. An ARL stands for Akamai Resource Locator. So these are actually special URLs that you use to construct, to kind of make references to files on Akamai's network. Again, this is like a deprecated style of doing things, but it's still enabled on many endpoints. So, say for example, you have this SWIFT and you want to, catch it through Akamai. You want to take advantage of this service. How do you do it? You remember that Akamai endpoint that we have here. We have akamai.example.com. You pass it a few parameters, things like how long should I catch it for? What's my client ID for billing? And stuff like that. And then you supply this arbitrary URL here where this file is located for Akamai to go off and grab it, bring it back, and serve it on your own page, right? So this example looks a bit familiar, doesn't it? So when Mike talked about SSRF, this is actually exactly the same flow, right? You have an arbitrary URL being specified, you have the server going off and grabbing it and returning it right on the page, and so perhaps there's an issue with this sort of functionality, and there was. So again, this is called Akamization of a URL, kid you not. And basically, this works by Akamai's big network coming and pulling that file and returning it on that page. So the vulnerability that we had was, if you point akamai.example.com to Akamai's Edge Suite kind of free flow service, we can actually host arbitrary files on that subdomain. So, but not quite. We actually ran into some issues when we were trying to actually practically exploit this. We saw this happening.
Yeah, so it depends on configuration. Like some Akamai endpoints just allowed us to load any files, but there was a much more variety of websites that allowed us to just load specific whitelisted domains.
Right, so we kind of noticed there's like a whitelist. We're like, all right, well, what's in this whitelist? How do we go about enumerating it? Any guesses? What tool we might use? Okay. So, while we're testing this out, we all right, well, let's try to load Google's robot.txt file. And when we tried to do that, we got an access denied error, which was like, why are we getting access denied for this arbitrary file as opposed to the other one? And so we kind of figured out, there must be some internal, whitelist of domains that is actually allowed to do this, right? So we set it up, we used subroot, and we tried to find, this is edgesuite.net, this is Akamai's domain. And we tried to find subdomains because we kind of figured that maybe one of those would be actually whitelisted and we could use it to push content onto their site, right? So after some searching with subroot, some Google lurking, we found an actual endpoint that worked, and this is it.
Boom.
Any thoughts on why this might be problematic? Yeah, I know, the flow player example wasn't just arbitrary. So this is an actual server that Akamai runs called mediapm.edgesuite.net, and this hosts not only remember the 3.2.18 that implemented a couple verification things that we were able to bypass. Yeah, none of that was even required because they hosted all the old versions too. So we could just pull the 2.16 version and just didn't even matter anyways. So what this means is, right, we putting all this together, we can actually put this SWIFT on your Akamai endpoint and then immediately hijack it with the vulnerabilities we talked about before. So here's an example of that happening, right? We have i.legitbank.com, which is mapped to Akamai's service, and then we specify this weird ARL style syntax, and we specify this 3.2.16 vulnerable version of flow player. And when we do this, it actually appears like the site is hosting the file itself, which is great for us because we can hijack it. So what does this mean on a grander scale? So this means that any endpoints that are mapped to Akamai service that use this free flow or have an insecure configuration, right? They're all vulnerable. We can load SWIFTs on them. We can hijack them. So it's a bit complex. We're going to go through the flow one more time. We have the user logging into Legit Bank. After logging in, they kind of navigate around, and they eventually hit our attacker payload, right? The attacker payload goes off using this ARL, ARL everyone style addressing, and we load the SWIFT. We tell Akamai, we want this file. Akamai goes off to this mediapm.edgesuite server, grabs the SWIFT, returns it as if it was hosted on akamai.legitbank.com, and that, of course, gets included on attacker.com on that web page, right? So it's almost as if they had hosted the file themselves, so we can still take advantage of the vulnerability. So then, of course, after that... Right, so that's just, they don't have to have Legit Bank opened up in their web browser at all, actually. Yeah, they just browse to our attacker site, and this happens in the background with.
They do need to have a current session, so they do need to be logged in, but they don't have to have both tabs open.
Right, so they just have to auth first. And so, as we saw before, we hijacked this SWIFT, and now we're executing in the context of akamai.legitbank.com. And remember I talked about earlier cross-domain files doing this wildcard subdomain thing? Well, guess what this is? This is a subdomain of legitbank.com, which of course is trusted by 75% of whatever websites, right? They trust all their subdomains. And then we can go right back and completely fine. We can grab all the content from legitbank.com. So we can go off and we can send money to my Nigerian friend. We can, change your finances up, wreak havoc, whatever you get your kick from. So let's go back. I've talked about cross-domain policies. We're going to go back to them real quick. So remember we talked about this policy earlier. What does this look like now? So we're actually pretty bad off, right? So if any one of these subdomains of either legitbank or thirdparty.com is mapped to an Akamai endpoint, we can basically compromise the security of legitbank.com. That's a bad deal because Akamai is like a very prevalent CDN, right? And this opens up some even greater implications where you may have never even heard of Akamai, right? But if you trust them via your cross-domain policy, your security is compromised anyways, right? They can still perform this exploit. And so due to this convention that's used in cross-domain.xml, you kind of have this impact, like it exponentially increases, right? So what's the fallout? Like who uses CDNs anyways? Any of you Verizon wireless customers? If you know, they did reach out to us and we're like, we need to fix this. And like we got them patched before we did the talk, so it's all cool. They were awesome. So, here's an example of a user, just going about the daily business. In this case, this is the Verizon wireless business site. So this is like if you have a company and you want to manage a bunch of phone numbers via Verizon, you use this portal to log in, delete phone numbers, look up personal information of all, whatever you want to do, right? So the user signs in just like they normally will, and, they come across this page, but then later on, of course, as we saw before, they end up navigating to a third-party attacker-controlled site, right? So we're going to see this example here where after they've authenticated, they just browse the internet as they would normally, and then they come across this site that has this exploit. So here's the example here. They navigate to this third-party website. This website embeds the SWIFT and hijacks it. One of their subdomains was mapped to Akamai. And because of that, because they trust all subdomains via their cross-domain, we can now hijack that SWIFT, go off to Verizon, grab your phone number data, pull all the SIM information, basically all the data from the account, do anything as you, right? And this is kind of the widespread impact that we see. We have another example here. Are there any NoScript users here? Don't not raise your hand because there's going to be a bypass. Good. For those of you that don't know, right, NoScript is a sweet add-on for Firefox that basically prevents, these, normally when you browse the web, JavaScript can execute, Flash, whatever, can just go ahead and execute right away. NoScript actually prevents that, so you have to actually give explicit consent before these things actually run, because they're often quite dangerous, right? There's like a Flash vulnerability all the time. You want to browse safely. But one of the things that a lot of people don't know about NoScript is when you actually download the extension, it comes preloaded with a whitelist of domains. And these domains actually, have a bunch of subdomains as well. They're all trusted. And so, of course, what are the bet that one of them is mapped to Akamai? The answer is absolutely. So just because they trust all the subdomains of these sites, just one of them had to be mapped to Akamai to use this vulnerability to load content on behalf of that domain, and we can completely bypass NoScript. So even if you're using NoScript, it doesn't matter. We can bypass it anyways and still exploit you using this, right? So content security policy, super awesome. It's kind of a new way to prevent cross-site scripting by preventing inline JavaScript on your page, right? Like you can only reference, you have to do external script tags for everything. It's great for preventing things like cross-site scripting, but unfortunately it's absolutely useless here because we don't even, we're not injecting anything into your page. We're actually taking your SWIFT, pulling it into our own page, and then kind of hijacking it, right? So CSP doesn't even apply here. Even going even further with this too, in CSP you can define a list of trusted domains, right? So even in this scenario, what if that trusted domain is mapped to Akamai? We can bypass it anyways, right? So there are a bunch of wide-reaching implications for stuff like bypassing CSP. I know I had a question on Twitter recently that was does sub-resource integrity, which is kind of a new standard, does that help with this? The answer is no, because we actually take the SWIFT, pull it on our own page, and hijack it. So remediation, if any of you guys are Akamai customers, I'm sure you're like, oh crap, we need to fix this, right? So Akamai has been awesome. They've been super supportive throughout this whole thing. This is actually, they were super nice about fixing this, and they wanted to work together. So in order to address this vulnerability, they've provided us kind of some remediation steps that you can go for.
They were super helpful, but so the night before we were giving our Black Hat talk, we were like refreshing our client pages, and they were all still affected. And something like 8 hours before we went on stage, they started rolling out patches. And like we couldn't go on stage unless they fixed, and they fixed at like the last possible minute. And so thank you, Akamai. But yeah.
Yeah, I'm not saying they didn't make us nervous, but they did fix it in time. So, right. So, say you're wondering like, how do I remediate? First thing you should note is like you may already be patched. So Akamai started doing like advanced things. They were trying to figure out like who can we just like turn this ARL functionality off for and still have nothing broken and fix this vulnerability. There's actually a large portion of customers that they can't do that for because they use this deprecated style. It's kind of like they depend on it, right?
Which creates kind of like a slow burn. Like this issue is something that's going to be around for a while because they can't fix it across the board. There are going to be a large number of sites that may be affected for even the next decade. Like there's no time frame on when it will be patched. Like a large number of people are patched, but not everyone.
Right, so that's important to take into account too, right? Like if you're doing a pen test, you should be looking out for this sort of thing, this weird addressing style, right? So if you are an Akamai customer, you're super concerned, you can actually call them at this number, email them at this email address. They actually have a playbook that their support agents have that's just about this vulnerability. So they hear you calling in, they'll be like, oh, I got this, and they can handle it appropriately, right? Also, they wanted to let you guys know that any public inquiries can be directed to Rob Morton, this phone number, this email address, if you're kind of interested in it in general, or talk to us either way. So they also wanted to let you guys know that they encourage security research on the Akamai product. If you find any vulnerabilities, like hit them up at security@akamai.com. If it's sensitive and you don't want anybody else reading it, use PGP. They were super helpful with us to be helpful with you. Akamai also wanted us to let you know that they're hiring folks for security, so they need smart people, right? So.
We're also hiring at Bishop Fox. We're looking for penetration testers, and here's our contact information. And thank you. Thank you, Derbycon.
So that was kind of a complex exploit chain. Are there any questions that you guys have about how this works, how you can get a patch going? What's up?
I'm curious when you're violating the same order or not violating, using the same
No, it's violating.
violate the same origin shenanigans there. Are you having to operate everything within the Swift, or how does that work a little bit? When you violate the same origin and you include and you go out and make those requests, do you have to have all your instructions within the Swift or in your page?
Yeah. So one of the things important to note here is we're not actually violating the same origin policy the way that this works, right? Because when we hijack it, it's actually executing in the same origin as the right. So all of the Yeah. So Flash is used for this whole shebang, right?
However, because of this atomization, you can also load HTML files, and so it is possible to load HTML or arbitrary binaries through this atomization SSRF vulnerability.
Right. The reason we use Flash is because it actually amplified our attack, right? Because there's so many cross-domain files with wildcards in it, we were able to expand our attack surface.
Oh, they're up on Bishop Fox's blog.
Great question. Yeah.
There should be exploit code public as well.
Yeah. If anybody didn't hear that, you can just go out to bishopfox.com and grab these slides as well.
When they're at the web pages, you can go just see if it works on your machine. You can some of that up. Like the no script one that you just click like a link for yourself to see that.
Yeah. So
They fixed
They fixed a lot of these.
Okay.
Yeah, so all the people that we know are affected are patched.
Okay.
So, yeah.
we need to tell Akamai about all of them.
Yeah, we had to give them the full list.
We can hoard them. might look a little dishonest. So, there may be other endpoints you have to find yourself.
Right. Thank you.
Cool. Thank you, everyone.